Hello SC students, let us start with chapter 1, Work and Mechanical Energy. Have you ever practiced bungee jumping? In fact, a jumper trusts an elastic rope and the laws of physics to perform astonishing adrenaline-rising jumps. When you do a bungee jump, usually gravitational potential energy, elastic potential energy, and kinetic energy are all demonstrated in one place. How's that? And how do we apply our lesson into bungee jumping? We'll see later on during the chapter. To move, a car also produces mechanical power. In fact, the car converts chemical energy into mechanical energy. As this is done, some heat is also liberated to the surrounding. Linking and relating these energies together is a main part of this chapter. Last but not least, when a rocket is launched to space, fuel combustion supplies it with enough thrust to launch. After that, internal energy decreases in order for kinetic energy and gravitational potential energy to increase. We'll talk about these in more details as we start. In this chapter, the main ideas are to talk about work, recognize potential energy and kinetic energy, and then calculate mechanical energy. This chapter is divided into 7 subtopics. These topics are work of a constant force, work of some particular forces, kinetic, potential, and mechanical energies. These 5 sections are mere vocabulary. When we go to section 6 and 7, conservation of mechanical energy and non-conservation, we go more into using this vocabulary in word problems. Let us start with the work of a constant force. In common language and daily life language, we use the term work to describe some effort done by man. Okay, sometimes work can be some fatigue done by man. However, in physics, it has some different definition and some different meaning. What is this meaning? Before we answer that question, let's observe these two situations. In the first situation, a man or a person is trying to push a wall. Definitely he won't be able to do that. So no matter how much force the person applies, he fails to move the wall. The force he is applying has no effect, therefore the person gets tired and no work is done. While in the second situation, you can observe a horse just pulling and towing a certain carriage. That is, this force, the force that the horse is applying, was able to move the carriage. So here, yes, the force has some effect and we can talk about work. So work of a constant force, if you just observe this figure here, work of a constant force is the energy it consumes or produces while moving from one point to another. Mathematically speaking, the work of a constant force is given by the equation work of F equals F dot AB, scalar product. If you remember scalar product from mathematics, it's fine. If you don't, it's simply F times AB times cosine the angle between F and AB. And I have some good news. We are just interested with forces that are parallel to displacement. So we won't have any angle in between. Okay, we'll just have the angles either 0 or opposite. Now, if you know some mathematics about trigonometry here, you will know that if alpha is 0, that means the cosine is +1. And in this case, we have the force and displacement in the same direction. Therefore, the work of the force is F times D. Whereas if the force is opposite to displacement, we just add a negative sign and we'll have work of the force equals negative the magnitude of the force multiplied by the distance. Now, moving to the second section, which is a direct application of what we have seen before, but since we deal with some forces regularly, it is important that we memorize the equations of the work done by these forces. Of these common forces, we have the weight, the normal reaction of a certain support, and the frictional force. Over here, if you look at the figure, you notice that there is a box. That box is assumed to be moving from A to B. A is up, B is down. The work done by the normal reaction is always zero. The reason is that the normal is always perpendicular to the motion. The second equation that we need to know is that of friction, the work of friction. The work of friction upon sliding from point A to point B is negative the magnitude of the friction multiplied by the displacement itself. Third is the work done by weight. This is a bit complicated if you go to the derivation. However, we do not need to worry about deriving the equation. Work of weight is simply given by mgh, where h is height A minus height B. Pay attention here, we are moving already from A to B. If we are moving from B to A, that differs. Nevertheless, so here, if I just want to consider what is h, it is this h that you can see in red on the figure. Now, you can always distinguish between two situations. If we are moving from A to B, from up to down, we use plus mgh. There is positive work. If the box or the object is moving from below to up, from B to A in this scenario, the work done is going to be minus mgh. Here it's important to mention the term that work can either be motive, which is positive, or resistive, which is negative. Now, why do we call it motive, or why do we call work resistive? That depends on what we might study later, which is known as kinetic energy. We will deal with these later. We will mention these vocabularies again. Nevertheless, for the time being, we just need to know the equations of the work done by these particular forces. Now, to make sure that you got these points and you know how to use the equations that we just mentioned, solve this application and you will find the solution in the last session as we finish all the course parts. That's all for the first session. Thank you for your time and see you in session 2.